In this video, I'm going to discuss about the properties of alkenes under the chapter 5 of acyclic hydrocarbons pulled out from the degree first semester syllabus. The whole chapter is being uploaded in my channel and the details have been given under the description below. Please you can go through it and subscribe my channel. And let's see this alkenes. It's know that it's an unsaturated compound. So the main characteristics of this is electrophilic addition reactions, because here it acts as a nucleophile, its electron rich, so act as a nucleophile, and the electrophile can come and attack this pi bond. So the electrophilic addition reactions might take place and the unsaturated compound is converted into an saturated alkane here. So the catalytic hydrogenation is the main property of this alkenes, and this pi bond which is seen here is converted here into the sigma bonds in the product here. Let's see this hydrogenation in detail. Now this catalytic hydrogenation is nothing but the addition of the hydrogen to alkene in the presence of nickel, palladium or platinum catalyst, and the hydrogenation will take place at the surface of the metal catalyst here. And the temperature in this particular case for the conversion of ethane to ethane is 150 degrees centigrade, and the pressure temperature differs depending upon the nature of the substrate and the nature of the catalyst which is used here. So different temperatures are being used for the conversion of these alkenes into the alkanes. And when we see the example of this trans to butane into butane for the conversion of this pi bond into a saturated compound, the palladium catalyst is used at 25 degrees centigrade and 3 atmospheric pressure, and for the conversion of the cyclohexene into cyclohexane, the palladium catalyst is being used at 25 degrees centigrade and 3 atmospheric pressure. And let's see this mechanism in detail now, what happens here. See, first of all, this alkene is being dissolved in solution of alcohol or acetone, and the reactant solution is being formed here. So this is in the solution phase now, and then the little of this nickel or palladium or platinum catalyst is being added, and then the hydrogenation will take place at the surface of this metal catalyst. First the hydrogen will get adsorbed onto this metal catalyst. So now this hydrogen is available for hydrogenation as hydrogen atoms, and then alkene is adsorbed onto the surface of the metal catalyst now, and then the step by step the hydrogen is being added one by one to this alkene, and the unsaturated is being removed. So the second hydrogen atom is transferred to the alkene. In this case, the first hydrogen atom is transferred here, and saturated compound is being formed here. And as addition is taking place from the same side of the molecule here, that is syn addition is taking place here. So the cis product is being formed here in this reaction because the addition is taking place from the same side of the molecule. And this is called as heterogeneous catalyzed reaction because the reactant solution is in the solution phase and this one is in the solid phase. So since the phase is different, the solid catalyst is in the different phase from that of the reactant solution, it is called as heterogeneous catalyzed reaction in the presence of a catalyst. So let's see this graph here and know the activation energy which is required here. The activation energy which is required when catalyst is being used is this violet line, and this green line is nothing but when catalyst is not being used. We can clearly see that the activation energy which is required here when catalyst is being used is much less when catalyst is not being used. So this is the difference in the activation energy when catalyst is being used and not being used. So the catalyst is being used in order to reduce the activation energy of the reaction, and we can clearly see that the products are at the lower energy level when compared to that of the reactants here. So this is the energy which is released when the hydrogenation is carried out. So this is an exothermic reaction because energy is released here, and the heat of hydrogenation which can be represented by delta H here is minus 20 to 30 kilocalories per mole. because here minus because the energy is being released, so the minus sign here. So depending upon this heat of hydrogenation values, we can arrive at the stability of the alkenes. Let's see the stability now, how it can be evolved depending upon this heat of hydrogenation values. For 1-butene, in the presence of platinum catalyst, when the hydrogenation is being carried out, the amount of energy which is released is 30 kilocalories per mole. And when cis-2-butene is converted, it is 28.6. When trans-2-butene is converted into butane, that is 27.6. So the energy which is released here is different when compared to when hydrogenation is carried out. So the heat of hydrogenation can be used to evolve at the stability of the molecules. How? See, the energy which is required for the conversion of this 1-butene to butane is 30.3, that is minus because it's exothermic. And which means that the energy which is associated with these molecules is more. That is why this more amount of energy is needed to convert into the product here. And this one, that cis-2-butene, is less than that of this butane here, and it's only 28.6, which means that this is more stable when compared to that of this, and trans-2-butene is even more stable than cis-2-butene. So the heat of hydrogenation values is inversely proportional to the stability. Yeah, you can understand this more by means of this diagram here. The heat of hydrogenation here, which is required for conversion of this is trans-2-butene. This is cis-2-butene, and this is just a butene here. So the energy which is required for this to convert it into a product, that is butane here, is more in this case of 1-butene, and here it is only 28.6, and here it's only 27.6, which means that this is at the higher energy level. So because it is at the higher energy level, the heat of hydrogenation, or the energy which is required to convert this, is more, and this is little more stable than when compared to this 1-butene. We can see that this is more substituted here. So the energy which is required here is less, and this is also disubstituted, but it's in the trans position, which is more stable when compared to that of the cis, because of the repulsion is less here. So the energy which is required is less. So this is more stable when compared to that of this, when compared to that of butene. So we can arrive that the height of hydrogenation values is inversely proportional to the stability. So depending upon this height of hydrogenation values, we can arrive at the stability of the molecules. So the lower the numerical value, depending upon this numerical value, we can arrive at the stability. So the lower the numerical value of the heat of hydrogenation, the more stable is the molecule. And we can know the substitution also from this. Depending upon the substitution on this alkene, the heat of hydrogenation values differs here. So large heat of reaction indicates a high energy reactant. That means the energy which is associated with the reactant is more. So more energy is required to convert into the product. So this is inversely proportional to the stability. Yes. Now when we see this, the stability of and the heat of hydrogenation, it is tetra substituted, that is completely substituted, which is more stable and more stable and less heat of hydrogenation. Because it is more stable, the heat of hydrogenation which is required to convert into a butane, that is heat of hydrogenation, is less when compared to that of a tri-substituted, which is less stable, and the heat of hydrogenation is little more. Then comes di-substituted, then comes mono-substituted, then comes unsubstituted. So the stability increases in this order, and the heat of hydrogenation increases in this order. So as the stability increases, the heat of hydrogenation decreases. That means less amount of heat is required to convert this into a product, because the energy which is associated with this reactant is less, because it is more stable.